Okay, so we're talking about curvilinear coordinates in general, and we want to do integral and differential calculus with them. And what we have so far is this realization that, let's just consider a line element, and you can do this with surface and volume elements too, of course, is that in Cartesian coordinates, everything's kind of done for you because the units of dx, dy, and dz all have units length, or in real dimensional analysis notation, we would say the units of dx are L for length, right? Which is okay, I can add length to length to length. But clearly I can't just take the coordinates, differential changes in coordinates, and then multiply them by the appropriate unit vectors. The unit vectors are fine if I'm thinking about spherical polar in this case. But this term, for instance, doesn't quite work because the units of d theta are in radians, so I can't add the length units to the radians unit, so apples to oranges. So what we know at this point is that each of these needs to have an appropriate set of scale factors. So if I really did want to write the line element in spherical polar coordinates, the d rho is okay. I'm calling it rho instead of r because I have an r there. And then I have rho d theta, theta hat. And then the geometric argument, you got to project down into the xy plane, rho sine of theta, d phi, phi hat. So correct units of length because of the rho correct units of length. And in general, we can write in some coordinate system any line element like this. So we'll call it h1 dq1. q1 hat. So q is the coordinate and h is the scale factor, and then h2 dq2 q2 hat, where h2 is the scale factor. In the case of Cartesian coordinates, the scale factor is 1 and q2 is y, and then the scale factor h3 is 1 and then q3 is z. In the case of spherical polar coordinates, the scale factor is rho sine theta, and q3 is phi. Okay? So this is the most generic thing that we can write for any orthogonal coordinate system, so any set of mutually orthogonal coordinates. And then in that notation, we have things like, I'll just write d tau. D tau would be h1 times h2 times h3, just associating a little bit, dq1, dq2, dq3. Okay, so you're tempted to just kind of run with this, and I'll write this as a question so that you're not really tempted to think it's correct, is that imagine that I wanted to write the divergence in curvilinear coordinates. So I've got some vector function v, and I want to write its divergence. And what I know is that every time I take a derivative, I reduce the power of each of the component functions by one factor of length, which is to say, as a little sidebar, df dx is the units of f divided by length, right? So every time I take a derivative, I go from, for instance, x cubed to x squared, x to the minus 1 power to x to the minus 2 power. So I know that I would maybe have to put a scale factor downstairs. And naively, I might write this. So I might write that this is the divergence. So it might be, okay, d by dq1, v1, d by dv, or dq2, v2, dv, dq3. And now we're not going to fall into this trap again. I know that q1 and q2 and q3 might not by themselves have the right units. So I might say, aha, maybe I have to do this. And what you can see is that if you took, for instance, one of the most divergent things that you could think of, which is, as an example, maybe I want to write the vector field k, well, write some constant alpha, r hat. Right? So this is a vector field that just bristles, constant vectors, but they're all radially directed. So they're all pointing away from the origin. And yeah, this thing looks like it should have a divergence. But clearly, these are just constants, and if I tried that, I would get 0. So this formula is not right. So the naive divergence formula isn't correct. And what we're going to do is we're going to prove the correct formula. So cross this out. This is wrong. It's not as easy as we'd like to believe. And I'm going to show you how you would prove this, and then I'll just kind of like hand wave. Similar thing happens with the curl, because this does get a little bit intense. But we proceed in the same way that we proceeded when we showed the relationship in between the two limiting forms of the gradient. So derivation of the curvilinear divergence formula. And we'll start with a nice big box. And we got to put a point dead center and then talk about how we're going to move it somewhere else. So this point is in the center of the box. You know, my artistry is only so good. And it's got coordinates q1, q2, q3. Right? And then the sides of this, so q's are the coordinates. I'm going to write s, because this is an actual length. So this is ds1, and it's got units of length. It's not dq, because that could be like, for instance, radians. It's ds, and that would hopefully have units, meters, if we were in SI. So these are actual unit-bearing lengths, the s's, whereas the coordinates are q. We have to keep that straight in our minds, because what we need to do is figure out what q is. Right? And then what we're going to do is appeal to our fundamental definition of what the divergence is. So the divergence is given by the following nice coordinate-free formula. Let's use A, so let's use V. And this is evaluated at Q1, Q2, Q3. And this is equal to limit as some tiny piece of volume denoted tau goes to 0 of the flux through the surface. So this is a Gauss's theorem type integral, or Gauss's law type integral too. Right, so this is the fundamental geometric definition of what the divergence is. So it's the limit as we take the flux through the surface divided by the volume of that surface. Okay, and what we have is part of this kind of for free, because we know what tau is. So this is going to be a limit as delta tau goes to d tau, and we know what d tau is already, so we've got that going for us. D tau, it's got to bear units, so it's all 3 scale factors times all 3 dq's. So I'll write it out in 2 steps just to remind everybody. This is what, these are all unit-bearing things, right? The ds's. And what that is h1 dq1, which might not, the q's might not bear units themselves. Okay, and this is almost too much. Okay, however you want to write it. And at some point, maybe we'll write it with the product symbol pi. Okay, so that we have, great. So that's the denominator. All we really need is the numerator. And of course, left that for last because that's the pain in the butt part. So what we're going to do is the same thing that we did when we proved the equivalence of the component form and the geometric form of the gradient, which is to say we're going to take all 6 sides of this box, and then we're going to move the function, the vector field, evaluated at here to be evaluated at each of the sides. There are 6 of them. We probably won't write down all 6 terms, depending on how big the chalkboard is. And then we'll take a limit. Okay? So numerator. Numerator is this. And the numerator really is this in that little infinitesimal, soon-to-be infinitesimal box. it's the sum over 6 individual sides. Actually, this is approximate equals because I'm going to just evaluate these at a single point. So I'm just going to say I'm evaluating V at side j. And then we'll write out, at least for one or two terms, the coordinates. And then d sigma j. So this is going to change. This is going to be pointing in the negative q1 direction, positive q3 direction, negative q3 direction, negative q2 direction, and so forth. Okay? So let's just pick one matching pair. Let's call it left and right, because it's probably easier for me to draw. And the other two pairs, the y pair and the z pair, like the terms will match. You just permute the coordinates. So I'm just showing you how this will look and what sort of limits we'll get. So we'll just take left and right. So that and that. So the deal is we got to move the vector function or vector field to the left side and then evaluate this, and then the right side, and then we're going to add them up and see if anything really nice happens. Okay. So this is on the right side. So maybe I should draw it on the right side. So here we are, and we have ds2 and ds3. And then we have, maybe the vector field is coming out like this. Right? And maybe we have, well, we definitely have d sigma that's coming out like this, right? And so there's an angle in between them, and then we've got to express that either by taking the component dot product or with angles. And you can probably guess that we're going to do components because that's easier. Okay. So this is good notation. I'll just call this all RHS for right-hand side. So V RHS dot d sigma RHS is a subscript. Okay, what do we care about? Well, this points in the S1 or Q1 direction. So all we care about is the one component of V. So that was our dot product, and that was really easy. So it's just the first component of this, because that's where Q1 points. We're going to need to think about sign in a second. RHS, and then ds2, ds3. That's the area, the magnitude, that's the magnitude, ds2 times ds3. And then the question is, do we have a plus or minus sign? You tell me. So if V1 is positive and this is positive, that's what we have, so that works out for me. And then expressing the S1 and S2 in terms of scale factors. So I'll move this over here. V1, RHS, H1, H2, and really quickly suppress this, but realize that the scale factors themselves depend on the coordinates. For instance, the farther you are away from the origin, the bigger r gets in the conversion in between spherical, polar, when you're computing the scale factors for spherical polar. Oops, this is 2 and 3. dq2, dq3. Okay, so not so bad. Now what we have to do is realize that generically for these 1, 2, 3 formulas, so RHS means that I'm evaluating this at this point. Oops, sorry, the right-hand side, at this point. So generically, each one of these, I got a Taylor series out. So everything was really nice up until this point, but here's where I start getting a little bit scared. So generically, V1, H2, and H3 are functions of Q1, Q2, Q3. And so by RHS, what we really mean is that each one of them, f is just a stand-in for one of these three functions, needs to be evaluated at, well, what is the right-hand side? The right-hand side is Q1 plus 1/2 delta Q1, Q2, Q3. Right, so this argument should look familiar. When we talked about limiting forms, we moved one of these to the appropriate side of the box sequentially, and we did that by taking half of the distance. I'm calling it big delta, and I'm calling it d there, but you know, all we are is one limit away from equating the two. Okay, and so now I know how to Taylor's theorem this function so that it can be approximately evaluated over there. So that's f evaluated at Q1, Q2, Q3. It's evaluated at the center. And the correction for that is I've got to move this over by 1/2 delta Q1, right? 1/2 delta Q1, partial f, partial Q1. Okay, so I'm just moving coordinates. The scale factor is taken into account by the fact that we've turned our ds's, which have actual coordinates, or actual units, into dq's. Right, so this is just a coordinate q. So basically I do that, and then I have to do all of the Taylor expanding and all of the canceling. So I have 1, 2, 3 things to Taylor expand. Each one will get a term, or two terms, one that looks like evaluate at the center, and then plus delta Q1 over 2 partial derivative of V or H2 or H3 with respect to Q1. Okay, so I'm just going to say that happens. It's really uninteresting and not difficult calculation to do, just a lot of terms to keep track of. And then when you add them, what you get is something that looks like this. So all of the Taylor expanding will give you this after a little bit of canceling. So this is what we want. V LHS. So the LHS will be the exact same thing, except we have a minus sign instead of a plus sign. D sigma LHS plus V RHS, the right-hand side of that cube, dot D sigma RHS equals, and should see that there's some cancellation that went in there, d by dq1, v1, h2, h3, dq1, dq2, dq3, and of course, what you're saying right now is you're lying. I paused the video, I carefully worked it out. I did not get that. I got something that was a lot messier, but I had a couple of terms cancel. And I'm going to say, actually you did, because this is just a really nice way of writing what you got, where if you use the product rule, what you'll get is a partial v with respect to Q1, and then these two terms, plus partial H2 with respect to Q1, plus those two terms. And those are exactly what you get when you multiply out. So each one should have one of those and two of those before the cancellation. So this really is what you got. Okay, and then adding them all together, so this is for my left plus my right-hand side. So adding all together, so we do this again for top, bottom, and front, back. And what you can see is that you'll get the exact same thing, but you just permute the indices. You'll get sum of all 6 sides, v side j, d sigma j, which is approximately equal to this. This is what we want. This was the numerator in our limiting form of the divergence, is d by dq1, v1, h2, h3, plus, so that's that. Notice how this is a d1, dq, d3. And so will this. So if you're kind of a combinatorically minded person, you'll realize all you need to do is permute 1, 2, 3, and all the even permutations. So H1, H3, and then DQ3, V3, H1, H2. And I ran out of room, so times DQ1, DQ2, DQ3. Okay. So that is not a volume element. That is a volume element that's missing the scale factors. So when you put all of this back together, and we get the divergence formula, we have a partial cancellation. So for now, I'm just going to call this big red star. Equals. So that upstairs and then that downstairs, that's our little piece of volume element. Q's are going to go away and the scale factors are going to remain. So what we get at the end of the day, and this is curvilinear coordinates, del V. So at the end of the day, we're going to get this, write it in the way that I'm going to write it for the rest of the quarter. Sure. So we'll pull the scale factor all the way out front. So So not the naive formula, which is just put scale factors downstairs. So something else is going on. So essentially, we have scale factors in two places. So you have scale factors on the components themselves, and then scale factors at the end of the, after we take the derivatives. Okay, we'll do this as an actual example and calculate it. But we started this example of a spherical polar coordinate vector function that if we used our naive formula, it would vanish. So I'm just going to point out that it no longer vanishes. So if you just look at the first term, what would this look like, just the first term in spherical polar coordinates? Well, we have 1 divided by all the scale factors. So out front, that's r times, so that's 1 times r sine theta, so r squared sine theta. So that's our scale factor. And then we have d by dr. Sorry. And then we have the vector function itself, alpha, in the r hat direction. These are both 0, so I guess technically we are doing the whole thing. So v1 is alpha times the other 2 scale factors, r squared sine theta. So this is correct and this doesn't vanish. And that's good because we didn't want that to vanish. When you look at this vector function, a whole bunch of constant vectors all pointing in the radial direction in 3D. I expect this to have some divergence. This looks like a very divergency thing. Okay, so I am going to just describe how the curvilinear form works and put it up there. And then what we'll do in class is just get as many examples as possible. You are more than encouraged to prove this. So the way that you would do this is exactly the same. If you wanted to prove the curvilinear curl formula, so So at-home exercise, you might want to do this. So the one thing I would suggest is to make use of Stokes' theorem. Right. So we have something, and I'll draw it in a way that, yeah, this really does kind of look curvilinear, right? So this definitely doesn't look like rectangular coordinates. And we have some actual bit of length. Again, this is the important part. So ds2 is h2 dq2. And then we have an actual bit of length, ds3, and ds3 is h3 dq3. Okay. So first idea is remember that you have Stokes' formula at your disposal, and if you want to calculate a curl, you can do that by potentially, in this case, taking 4 elements of a line integral. So the second thing I would suggest is this is what we had to do with the divergence formula. Remember that both hk and vk change, right? So you have to evaluate hk and vk at their boundaries. So this might be v of q1, q2, q3. So you have to move that to the boundary when you take the line segment integral. But then you also have to move the scale factors because those are also functions of the variables q. So after you've written that out, use Taylor's theorem to move them up to their first derivatives, and then a lot of arithmetic. Okay. The reason we won't do this is because it's really, aside from realizing that you can actually use the line integral as well as just this whole wretched determinant of, well, actually, sorry, you have to use the fundamental geometric definition of what this is. Apologize for saying that. So you can use the fundamental definition of this geometrically, or you could use that. But the important part is you got to remember that when you move to the edges of the surface or the line integral, both of these things change. And the rest is just Taylor's theorem and a lot of algebra. Okay. And what you'll get is this. And as I write it, you'll realize why in a physics class, at least, we'll just say, like, I trust you. So this is the curvilinear formula for the curl. Okay, so that doesn't look so bad. Yeah, expected to have one of those. Okay, that's starting to look annoying. So you got scale factors on the unit vectors. And there are other ways of writing it. This is a way of writing it that keeps at least the partial derivatives looking kind of clean. So I prefer this way. And then h1, v1. Right, and essentially what's happening is just like in the divergence formula, you get 2 scale factors and then v, and then you have 3 scale factors divided afterwards. But now they're being mixed because you have a curl. So this is the curvilinear curl formula. We'll do 1/2 example is what would this look like for polar coordinates? Actually, let's do cylindrical. We haven't done cylindrical in a while. So in cylindrical polar. Okay. So our coordinates in cylindrical polar are rho, phi, z. Our scale factors are 1. That's already in units length. Rho, we need to multiply that by rho to get the arc length. And then 1 because z is already in units of length. So really not that bad, but that would make the curl of a vector function expressed in cylindrical polar coordinates. 1 divided by 1 times rho times 1 is rho. And then that's just rho hat times 1. That's rho times phi hat. And then that's 1 times z hat or k hat. We'll use k hat. This is the nice part. D by d rho. I'll let you use this notation if you'd like. I like it. And then scale factor is downstairs too. So then that's v1 rho times v2 and then v3. Or we could also write this v sub rho, v sub phi, as in the phi component, the rho component, and v sub z. Okay. So voila, this, the point is this is not obvious. I don't know if this would occur like, oh, of course, that's the curl in cylindrical polar coordinates. So in class we'll do examples. Great.